In this video, we will talk about bases for subspaces. First, we will review the idea of a spanning set, and a set of vectors span a set W if every vector in W can be written as a linear combination of your set of vectors. Next, we will talk about minimal spanning sets, which will lead us to the definition of a basis. And a basis is a linearly independent spanning set, and is also, in some sense, a minimal spanning set. We will talk about a procedure for getting a basis when you are given a spanning set, and then a theorem which gives you an alternate procedure for finding a basis. To review spanning sets, so if W is a subspace of Rn, and S is the set of vectors W1, W2 up to Wm, and it's a subset of W, we say that the set S, the set of vectors, is a spanning set for the subspace W, or we can also say S spans W, if every vector in W can be expressed as a linear combination of our spanning set. Another way to express this or denote this is span of S is equal to W. Our first example of a spanning set is the natural basis or the standard basis E1, E2, E3. Those are the vectors that have 1 in the ith position. So E2 has the 1 in the second position, etc. And this is a spanning set because a spanning set for R3 because any vector ABC and R3 can be expressed as a linear combination of E1, E2, and E3. The first coordinate multiplied by E1, the second coordinate multiplied by E2, and the last coordinate multiplied by E3. U1, U2, U3 is also a spanning set for R3, where U1 is 1, -1, 0, -2, 3, 1, and U3 is 1, 2, 4. To show that U1, U2, and U3 is a spanning set, we must show that an arbitrary vector in R3, so we'll just name it with A, B, and C as coordinates, can be expressed as a linear combination of U1, U2, U3. In other words, x1, where x1 is a scalar, times U1 plus x2 times the vector U2 plus x3 times the vector U3. And to figure out if A, B, and C can be written as a linear combination of U1, U2, U3, we just need to solve the matrix equation of AX equals V. So V is our arbitrary vector in R3, and the matrix A is just the column vectors U1, U2, U3. Here we have our augmented matrix, which is row equivalent to this matrix, and then we solve, and we see we can find a solution that x1 is equal to A minus x2 minus x3, x2 is equal to minus x3 plus A plus B, and x3 is equal to minus A minus B minus C. So every vector in R3 can be expressed as a linear combination of U1, U2, U3, and therefore U1, U2, and U3, the span of those three vectors is equal to R3. Another example, do the vectors V1, 1, 2, 3, V2, -1, 0, -7, and V3, 2, 7, 0 span R3? And again, the question of span is, can every vector in R3, which we will represent with the vector ABC, be expressed as a linear combination of V1, V2, and V3? We take the augmented matrix, which is row equivalent to this matrix, which tells us we have solution only if minus 7A plus 2B plus C equals 0, and A equals 2/7 B plus 1/7 C. So for example, if I plug in, if V equals 1, 1, 1, we cannot express this as a linear combination of V1, V2, V3 because A, which is 1, and B, which is 1, and C, which is 1, would give us minus 7 plus 2 plus 1, and that does not equal to 0. So V1 does not fit the solution space of our augmented matrix, and therefore this cannot be expressed as a linear combination. And so our conclusion is V1, V2, and V3 do not span R3. Our next example is given a matrix A. We want to exhibit a spanning set for the nullity of A, or the null of A. And just as a reminder, I have the definition of the null space or the kernel of A, and those are the vector x such that AX is equal to 0. I have my augmented matrix A here and my 0 vector here, since we're looking for where AX equals 0. I've done the elementary row operation, so this is the row equivalent matrix. And sometimes I put the x1, x2, x3, x4 just to remind me this is the column that multiplies by x1, this is the column that gets multiplied by x2. But anyway, what I can see here is that x3 and x4 are free, that x2 will be equal to negative x3 plus 2x4, and x1 will be equal to negative 2x3 minus 3x4. So these are the solutions for the null space when we want to have a solution for ax equals 0. So the null of A is equal to x such that, and then I plugged in my x1 minus 2x3 minus 3x4, plug in my x2 minus x3 plus 2x4, x3 and x4 are free. So another way of looking at this, I can look at all the terms, all the coordinates that have an x3 in them. So I have a minus 2x3 here, a minus x3, and a positive x3, and then nothing in the last coordinate. Then I can look at all the coordinates and see how they relate to x4. So I have a minus x4, I have a 2x4, I have a 0 here, there's no x4 here, and then I have a single x4 here. So I can take these two vectors and make them a linear combination of x3 and x4. So I would get the minus 2, minus 1, 1, 0, minus 3, 2, 0, 1. So this means my solution space, or my null of A, is going to be spanned by these two vectors here, my negative 2, negative 1, 1, 0, and negative 3, 2, 0, 1. Again, that will be equal, the span of these two vectors is equal to the null of A. And just to kind of quickly review what we did, we figured out what the null space looked like, and this is what the null space looked like, and then we broke down this into a vector dependent on x3 and a vector dependent on x4. So essentially, if you look at this, the number of vectors you expect in your span is going to be equal to the number of free variables that you have. And then once you broke that out as x3 times a vector and x4 times a vector, you get your spanning vectors. Our next example, if A is an m by n matrix, give a spanning set for the range of A. And just a reminder of what the range of A is, those are the vectors y such that there is some x that you can find ax equals y. So in other words, I've rewritten it here, y is equal to ax for all x in Rn. And one more reminder, when we were working with matrices, we said that when we have this ax, we can when we do the multiplication, each row by column here, and then row by column, we can then write this as the first column of A times the first coordinate of our x, the second column of A times x2, plus the third column of A times x3, and then we denote the columns with the capital A1, A2, and A3. So that tells us y equals ax, the matrix ax, is equal to the column vector a1 times x1 plus a2 x2 plus a3 x3. In other words, y is spanned by the columns of A. Now that we've reviewed the idea of spanning sets, we want to look at the idea of a minimal spanning set. In particular, so if we have W, which is a subspace of Rn, then the spanning sets for W abound. In other words, once you find one subspace or spanning set, you can always just multiply your vectors by some scalar, and you'll have a different spanning set. So you can just keep going, and there's an infinite number of spanning sets. But what we want then is to find an efficient spanning set, and there could be more than one. And the key is that linearly dependent sets are inefficient, because linearly dependent sets contain redundant information. For example, we've seen the standard basis will span R2, so E1, 1, 0, and E2, 0, 1 will span R2, because given any vector in R2, which we'll denote as V1, V2, we can write V as a linear combination of E1 and E2. That is, V is equal to our V1 coordinate times E1 plus our v2 coordinate times e2. But we can also see the set 1, 0, 0, 1, 1, 1 also spans R2. Of course, you can see this pretty quickly because you only need these two to span, so this is extraneous. But we'll go through the entire steps of verifying that this also spans, and then we'll go through the step of verifying that there's redundant information. To start, we can see that any vector v can be written as a linear combination of the three vectors 1, 0, 0, 1, 1, 1. So I have my vector v, which I represent as v1, v2. I solved the augmented matrix, and I got v can be equal to 1, 0, v1 minus x3, v1 is being the first coordinate of my vector, 0, 1, v2 minus x3, and 1, 1, x3. And you can verify, you can multiply this out and verify this gives you v1, v2. So any vector in R2 can be written as a linear combination of the three vectors here. But we also see the 1, 1 is unnecessary because 1, 1 is a linear combination of 1, 0 and 0, 1. So we really can rewrite this and eliminate this x3 and 1, 1 vector just by simply writing v1, v2 in this form, this linear combination of v1, e1 plus v2, e2. For our next example, we have s is equal to v1 equals 1, 1, 1, v2 is equal to 2, 3, 1, and v3 is equal to 3, 5, 1. We want to show s is linearly dependent, and then we want to exhibit a subset T of s such that T contains only two vectors, but the span of T is equal to the span of S. To show they are linearly dependent, we take the linear combination and set it equal to 0. So then we have this augmented matrix, which we solve, and we get A3 is free, A2 is solved in terms of A3, and A1 is also solved in terms of A3. In particular, A2 is equal to minus 2A3, and A1 is equal to A3. So this means A3 is free, so we'll just leave the third vector here, 3, 5, 1. A2 is equal to negative 2A3. So here's our second vector, which we need to multiply by negative 2. And then last, we have our A1 is equal to A3. So we just put a 1 in front of it and put our first vector in there. So this tells us, and we can eliminate any one of these two. We can solve for any one of these vectors in terms of the other two, and I chose to solve for v3 in terms of v1 and v2. So that means v3 is equal to 2 times v2 minus v1, and you can verify this calculation. But you see that we can rewrite the third vector as a linear combination of the other two. So they are linearly dependent, which means we only need v2 and v1 to span the same set, because anything that depends on v3 can be rewritten in terms of v1 and v2. So T is just going to equal to 2, 3, 1, 1, 1, 1, and the span of those two vectors will equal the span of the original 3. And you can see, in some sense, spanning with using only two vectors is more efficient. And now we are ready to talk about a basis. So a basis for W is a linearly independent spanning set of W. So the two components of a basis is it's linearly independent and it spans. And so the idea is that a basis is an efficient way to span the set. So we have discussed E1, E2, and E3. These span R3 and are linearly independent and therefore a basis. I have another set of three vectors, 1, 0, 0, 1, 1, 0, and 1, 1, 1. I have the calculation to show that they span any vector with components A, B, and C over here. And then I also have shown that these three vectors are linearly independent, that the homogeneous equation has only the trivial solution. So this set here, the 1, 0, 0, 1, 1, 0, and 1, 1, 1, is also a basis for R3. For our next example, we have A is equal to 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, negative 1. We can compute the range, and I do it on the next slide, but this is something that we've done other examples for. we can verify the range is equal to b1, b2, and the third coordinate is 3b1 minus b2. Once we have the range, we might be asked to obtain a basis for the range. So this is what we're going to do next. Here I have the calculation for range that's simply equal to vectors y, that is the matrix A times any vector x. So here I have the matrix A, my matrix x gives me y, so I solve the augmented matrix and I get this solution here. Now to get a basis for my b1, which is b1, b2, 3b1 minus b2, I break this up so I separate b1 and b2. Then my first vector, I'm going to write everything that's multiplied b1 in my range. So the top coordinate is multiplied by 1. The second coordinate has no elements of b1, so I just put a 0. And the bottom coordinate has 3 times b1. My next coordinate, b2, there's no b2 in the first coordinate, there's 1 b2 in the second coordinate, and then here there's a negative 1 b2. So you can see that this linear combination of 1, 0, 3, 0, 1, negative 1 will span this range, this space created by the range. So this is the solution right here. And normally for a problem, this should be enough. But just to show you that they're linearly independent, you can take these two vectors, set them equal to 0, solve the homogeneous equation, you'll find only the trivial solution. And so therefore, these two vectors span the range and they are linearly independent and therefore a basis. And again, normally you will not have to verify they're linearly independent, so since you took these two free variables to make the two vectors. Another example, let W be the subspace spanned by S, and we have 5 vectors, 1, 1, 2, negative 1, 1, 2, 1, 1, 1, 4, negative 1, 5, 1, 0, 4, negative 1, and 2, 5, 0, 2. We want to find a subset S that is a basis for W. To start, to find a basis, we need to have two things. We need our set to span, and we need them to be linearly independent. Well, by definition, this set, the set of 5 vectors, will span the space we are interested in, so we need to find a linearly independent subset of these 5 vectors. To narrow down or to winnow this set to a linearly independent set, we saw the homogeneous equations, and this is the result. x3 and x5 are free. x1 is equal to minus 2x3 minus x5. x2 is equal to minus 3x3 minus 2x5, and x4 is equal to x5. And now I'm going to look at x3 and x5 separately, and by that I mean first I'm going to set x5 equal to 0 and x3 equal to 1, so that will allow me to focus on x3 because I set x5 equal to 0. And then the next step, I'll do the opposite. I'll set x3 equal to 0 and x5 equal to 1, so I can focus on x5. When I set x3 equal to 1, x5 equals to 0, I get x1 is equal to 2, just using this equation here. x1 is equal to 2x3, so I get 2. x2 is equal to negative 3, and x4 is equal to 0. So when I plug this in as a linear combination of my v1, v2, v3, v4, v5, I get 2 times v1 minus 3 times v2 plus 1 times v3 plus 0 times v4 and 0 times v5. So I'm left with this equation, so I can solve for v3 in terms of v1 and v2. And I could have chosen to solve for v2 in terms of v2 and v3, but here's v3 without a coefficient, so I thought that was easiest. Now when I solve for x3 equals 0 and x5 equals 1, I get x1 is equal to negative 1, x2 is equal to negative 2, and x4 is equal to 1. So I have my negative 1 v1, my negative 2 v2, 0 v3, 1 v4, and 1 v5. So I solved, and this time I chose to solve for v5, and I get a linear combination. v5 is a linear combination of v1, v2, and v4. Since v3 and v5 can be written in terms of the other vectors, that means they're kind of redundant information. So v1, v2, v4 which is 1, 1, 2, negative 1, 1, 2, 1, 1, and 1, 0, 4, 1, is a basis for W. It both spans and is linearly independent. So summarizing what we just did, if this helps you, I actually don't really use this, I just remember the definition. But if you're given a spanning set, you can find a basis. So one, again, we're given a spanning set V1 through Vm. We solve the homogeneous vector equation, and if the equation has only the trivial solution, then S is linearly independent, and hence your set of vectors is a basis. If the vector equation has non-trivial solutions, then there are non-constrained variables. Delete these vectors from the set, the corresponding vectors from the set, and the remaining vectors constitute a basis. So just to look at this procedure in terms of our last example, we had our V1, V2, V3, V4, V5. We set the homogeneous equation and solved. We got two free variables, which was x3 and x5. So those are the two vectors we can eliminate, and we're left with V1, V2, and V4 will be our basis. We have this next theorem, which will give us another way of finding a basis, and that is if a non-zero matrix A is row equivalent to a matrix B in echelon form, then the non-zero rows of B form a basis for the row space of A. So we're going to use this theorem now to find a basis. We're going to redo our last example where we had V1 equals 1, 1, 2, negative 1. V2 is equal to 1, 2, 1, 1. V3 is equal to 1, 4, negative 1, 5. V4 is equal to 1, 0, 4, negative 1. And V5 is equal to 2, 5, 0, 2. We're going to use this theorem now to construct a basis. Since the theorem talks about row spaces, we're going to use the transpose so that now our vectors v1, v2, v3, v4, v5 are the rows, and now we can consider the row space. So we look at v transpose, which again is v1 is over here in the first row, 1, 1, 2, negative 1. v2 is the second row, 1, 2, 1, 1, etc. We find that this matrix is row equivalent to the matrix 1, 1, 2, negative 1, 0, 1, negative 1, 2, 0, 0, 1, 2, and then zeros on the fourth row and zeros on the fifth. And we're going to call this matrix B transpose. And what we want to note is the non-zero rows of B transpose, which there are 3, form a basis for the row space of V transpose by this theorem here. These two are row equivalent, so the non-zero rows of B transpose form a basis for the row space of A. But the thing is the non-zero columns of B are a basis for W now. So to see that, we can look at B, which is just the transpose of B transpose. Now, these non-zero columns now are a basis for W, and that's because these rows, being a basis for the row space of here, and the row space is exactly, each row is exactly the column. So I can just rewrite this as the columns, and now these span W. And something to note, if you compare this basis to the basis we found in the previous example, which was just V1, V2, and V4, you will note we found a different basis now. So this method of finding a basis using this theorem will give you something different than just eliminating the dependent vectors. So in the same way I had summarized that procedure, I summarized that procedure here, which was written and finding a basis using this theorem. So first you're given a spanning set, you use elementary row operations on the transform, V transform, and you call that B transform, and then the non-zero columns of B, so you have to rewrite B, are the basis for W. So this is the procedure for finding a basis using this theorem. So now you have two procedures for finding a basis. So we've covered now the material for this video, which was basis. We reviewed what it was to be a spanning set. We talked about minimum spanning sets, and then we said a basis is a linearly independent spanning set. So to be a basis, the basis must both be linearly independent and span your set. we had two procedures for finding a basis. The first one is getting rid, if you're given a spanning set, to find a basis, you just need to get rid of some dependent vectors. And the second method was by using this theorem, at which I don't have room to write the procedure, but it was the handwritten one we just saw. For review, I have 4 problems for you to try. So pause the video, give the problems a try, and on the next slide, I'll have solutions for you. Here is the solution for problem 1. This is the solution for problem 2. The solution for problem 3. The solution for problem number 4, using linear combinations and eliminating dependent vectors. And a solution for problem 4 using the theorem. And that's it for this video. Thank you for watching.